Welcome to the Winds and Currents webinar. Today we have Tom Farrar, who's going to talk about the Sub-Mesoscale Ocean Dynamics Experiment, S-mode. And I'll let you take it away, Tom.
Okay, thanks, Sarah. Hello, everyone. So S-mode, or the Sub-Mesoscale Ocean Dynamics Experiment, is a large NASA-funded experiment. We have a huge science team, and many people have contributed to S-mode, and I have the honor of speaking for the team on this, and I've listed some of the people who provided material that appeared in this presentation. But there's a huge group of people who are making intellectual contributions to what I'll be talking about. So for this talk, first of all, I want to say that for those of you who were at the Philochange meeting, there's like 80% overlap on this talk with what I talked about there. So for your information, in this talk, I want to focus largely on the technological aspects of S-mode. I will start with a brief discussion of sub-mesoscales and the motivation for S-mode, but then I'll pivot to a lot of the technology that we're using, and especially comparisons between different methods of measuring ocean velocity. And I'll talk about our plans to focus on vertical velocity and gradients of horizontal velocity. And I'll show you some of the results from our pilot campaign that we conducted last year. So this image shows sea surface temperature from the Capet et al. Series of papers in 2008. And on the left, we have a relatively high resolution model at 12-kilometer resolution sea surface temperature. And the thing that people have known for decades now is that as we increase the resolution of these ocean models, we start to see an eruption of fine scale variability that we call sub-mesoscales at scales of 100 to 10 kilometers, or 100 meters to 10 kilometers. And we know that the sub-mesoscale eddies in these models do something important. They have a net transport, and they affect the horizontal and vertical structure of the upper ocean on much larger scales. So we believe that the sub-mesoscales have an important role in the ocean based on these simulations, but the simulations are really quantitatively questionable because a lot of what we're looking at are right at the limit of the resolution of these high resolution models. In fact, as we continue to improve or increase the resolution of these high resolution simulations, we continue to see SST gradients that are as sharp as the model resolution allows. So this is from the kind of latest incarnation of the UCLA ROM simulation. And you can see that really down to the grid size, we have very sharp SST gradients and formation of fronts. And so there's, while these simulations are really impressive, there's reason to kind of retain some skepticism as to whether this is entirely faithful, because we're we're operating right at the model grid resolution. And so a lot of these features can be sensitive to the model numerics and the parameterizations of small scale turbulence. So we need to have benchmark observational studies to kind of ground truth these model simulations. And one of the important ones was the LATMIX study, which was done more than a decade ago. And what they did there, among other things, was run 2 research vessels together along a parallel line at 1 kilometer horizontal separation. And so then with the ship's ADCPs, they made estimates of the vorticity and divergence south of the Gulf Stream, and employing a kind of frozen field approximation, they computed the 2D gradients from those 2 ships moving together, and were able to verify that a lot of what these high resolution models were showing is faithful in terms of statistics of vorticity and divergence. And so in S mode, what we're trying to do is really to go far beyond this. And I'll talk about some of the technological developments that we hope will allow a big step forward in measurements of vorticity and divergence and vertical velocity. So the purpose of S mode is to test the hypothesis that these kilometer scale ocean eddies make important contributions to the vertical exchange in the upper ocean. S mode is it was originally a 5-year program. It's been drawn out a little bit by the COVID pandemic. It started in 2019, and we conducted a pilot experiment about 1 year ago. And now we're starting our intense operations period. We have 2 of those. One will be in October of this year, and the next one will be in April of 2023. And we're using a combination of aircraft remote sensing and autonomous platforms, a research vessel. The autonomous platforms include surface drifters, Lagrangian floats, gliders, wave gliders, and sail drones. And the operations area is offshore of San Francisco. The aircraft measurements include Doppler scat and an instrument called MOSES that measures sea surface temperature with an infrared camera. The Scripps mass instrument, which measures a suite of parameters like sea surface height from LiDAR, visible and infrared imagery, hyperspectral imagery, and then the PRISM instrument, which is a very accurate hyperspectral imager. Okay, so I'd like to talk about some of the factors that enable S mode and make this a good time to push forward on measurements of velocity gradients at sub-mesoscales. So one that is really important is that there have been a lot of recent advances with acoustic Doppler current profilers and in situ platforms that allow measurement of vertical velocity now, and in general improved estimates of horizontal velocity. There are new techniques for aircraft remote sensing measurements of surface currents. And it was also really important that there was this opportunity from NASA to combine these remote sensing and in situ measurements with the Earth Ventures suborbital program. So I'd like to talk in more detail about the in situ and remote sensing measurements. So first, with the in situ measurements, there are several important developments of the last decade or so. First, there are now cheap surface drifters that can be deployed at large scale. There was a recent experiment that deployed over 1,000 surface drifters. We're not doing that in S mode, but we have on the order of 100 surface drifters to deploy in the upcoming experiments. ADCPs, the electronics have gotten a lot better. They're now available with integrated inertial motion packages that can improve the quality and the separation of the vertical and horizontal components in the velocity. And importantly, a patent expired on ADCPs that opened up the market to competition and has led to sort of faster sampling ADCPs with features like integrated IMUs. And then there have been continuous improvements of autonomous platforms, and now they're integrating ADCPs and nice IMUs to get higher quality velocity measurements. And finally, the development of Lagrangian floats with these new ADCPs allows direct measurement of vertical velocity. So the Lagrangian floats that were developed at University of Washington Applied Physics Laboratory by Eric DeSaro and his team have really are providing unique vertical velocity measurements that are relatively direct. Here's an example from a 2018 paper in the Cartha experiment. So the float was deployed here near the triangle, and you can see when it gets to this square, which is marked in each panel, the float subducts, and as it goes down, it has so it knows where it's at from the pressure, and it has an ADCP looking up, measuring the flow relative to the float. And so they were able to basically map the vertical velocity as this float subducts, the velocity is negative. We're seeing really large vertical velocities, like a centimeter per second. And the float goes around in this eddy and eventually comes back up. So another thing that we're making a lot of use of in S mode is arrays of autonomous platforms with ADCPs. So the idea here is to operate these autonomous platforms in arrays, like on kilometer scales, and estimate the velocity gradients, the vorticity and divergence and strain. And from the divergence, we can estimate the vertical velocity by integrating the continuity equation vertically. So here's one example. This is the implementation of a wave glider that was developed by Laurent Grar and Luc Linane and their team at Scripps. So the key things here are that they have ADCPs and a really nice motion package that has a dual GPS and an IMU that are integrated together to give very accurate estimates of the orientation of the wave glider. And so then every ping can be motion corrected and oriented to give a more precise estimate of the velocity. And so our group at WHOI and the group of scripts have been meeting every week for 3 years since the start of S-Mode, working together to try to dial in these platforms for S-Mode. And we conducted an experiment offshore of Scripps near Del Mar, and we put a bottom-mounted ADCP looking up in about 40 meters of water, and then drove the wave gliders back and forth over this for like a week. We had the wave gliders rotating through this pattern to get measurements in different orientations to the wave field. We're especially concerned about wave-induced biases near the surface. And the sort of short version of this is that we believe that the wave gliders have bias errors less than 1 centimeter per second and random errors of 1 to 2 centimeters per second. That's important because to resolve a divergence of 0.1 F at the latitude of San Francisco, you need an accuracy of 1 centimeter per second. So if you have 2 platforms 1 kilometer apart with a random error of 1 centimeter per second, you can resolve 0.1 F, which is like a small part of, a big vorticity or divergence signal would be of order F. So that would give us good resolution of the vorticity signals that we care about. So a bunch of the platforms in S-Mode have ADCPs, UWC gliders, the wave gliders, and sail drones. The sail drone ADCP and IMU setup is very similar to what's used on the wave gliders. And we think they have similar accuracy. And so the idea is to operate these in arrays to estimate the gradients of the velocity field and to deploy them together with Lagrangian floats and surface drifters, and then sample around all of these assets with the ship. So the other major innovation is the development of aircraft remote sensing measurements of surface currents. One of the stars of S-Mode is the JPL Doppler scatter instrument, which is a Ka band Doppler scatterometer, very similar to the concept for Odyssey. And the other is the Scripps MASS system, modular aerial sensing system, which includes an instrument called DOPVIS that I will describe and that Luc Linane described in more detail in a previous talk here. First, I want to give a really basic description of how Doppler scat works. Many of you know this much better than me, but I suspect some people on the call probably haven't seen an explanation of how Doppler scat works. So I'd like to go through that because I think it's really important for this audience. Scatterometers work because of Bragg scattering, which is like you send a radar pulse toward the sea surface, and you can get constructive interference of the backscattered radiation when the radiation is scattering off of features of a particular wavelength. And so that causes the returns to be dominated by this Bragg scattering resonance. So the radar is seeing is kind of most responding to a particular wavelength on the ocean surface. And wind scatterometers target Bragg wavelengths that are pretty short waves that are in equilibrium with the local wind. And then the backscatter radiation is related to the amplitude of these waves, which is related to the wind speed and direction. So here's an animation of QuickScat. It has a spinning pencil beam radar. And so it's going along, mapping out a circle, or, with a circle. And from that, you can triangulate the wind speed and direction. Or you get different measures of the backscatter at different directions, and from that you get the speed and direction. So a conventional scatterometer measures the amplitude of the backscatter radiation, and a Doppler scatterometer also measures the phase of the backscatter radiation. I'd like to just quickly show the sort of equation for the principle of measurement. So the distance from the radar to the sea surface could be measuring wavelengths. So the number of wavelengths for a two-way trip is 2r over lambda the wavelength. That number of wavelengths is equal to the number of complete phase cycles that's seen at the transmitter. And that, by equating those, you get this equation. So you have an equation for the range from the radar to the sea surface, and the radial velocity is related to is dr dt. So that radial velocity then is related to the phase change between two successive pings. And that's the basic measurement principle. It's also, by the way, the same measurement principle used by a lot of ADCPs and can be applied for HF radars. So the Doppler scat instrument is spinning, viewing this circle on the sea surface as it goes along. You can see the same spot on the sea surface from two locations and estimate the vector velocity. But at the very edges of the swath and the center of the swath, we get a sort of ill-conditioned inversion for the one of the two vector components, which you'll see in estimates of divergence and vorticity. So I want to point out that we're seeing because we're seeing these gravity capillary waves that are short wavelengths, there's a lot that goes into the speed of those gravity capillary waves. That's essentially what Doppler scat is measuring. Part of it is the phase velocity of those waves. To first order, we know pretty well the phase velocity of those waves through their dispersion relation and the knowledge of the wind direction. There's the orbital wave velocity, which you might expect to average out on kilometer scales, but there are subtleties related to the modulation of these short waves by the longer waves. In other words, the amplitude of the short waves is a function of the phase of the longer waves, which can introduce biases. And then there's advection of all of this by the surface currents, and that's really the residual that we want. As I mentioned before, the ADCPs, HF radars, and Doppler scat basically rely on the same measurement principle, but their scatterers are different and have their own dynamics. So we'll see some data from Doppler scat in a moment. I also want to describe mass and the .viz system that's part of that. So Luc Lenane has been working on this. What we're seeing here is an image of a visible image of the sea surface taken by MASS. Its camera's looking forward, and Luc is identifying these boxes, and within each of those boxes, there's like a video of the evolution of the wave field as it goes along. So it can take that video and do a multidimensional Fourier transform and basically see the gravity wave dispersion relation. But there's a shift in that dispersion relation due to the surface currents, and so he can invert to estimate the surface currents from the Doppler shifting of that dispersion curve. And then it can do it at different horizontal wavelengths, get the Doppler shift as a function of horizontal wavelengths, which gives some information about the vertical structure of the horizontal currents. And so here's an example of the velocity vectors from one flight of the MASS .viz instrument. Okay, now we'll come back and see more of data from Doppler scat MASS and the in situ instruments. But I wanted to just talk about the sampling strategy briefly, which is that will largely be focused on vertical velocity and the gradients of the horizontal velocity. We performed a smaller scale pilot campaign and are about to start intensive operations. Right now we have 13 gliders and 7 wave gliders deployed in the S-mode area, and there are sail drones waiting to turn on their data streams in a week or so. So there are several formal science objectives for S-mode. One is to measure the 3D structure of sub-mesoscale features. Another is to understand the relation between velocity and that's measured by remote sensing with that compared to the velocity measured just below the surface. And we've done a lot of work on this second goal in the pilot campaign. And then the goals that are listed in green are a bit more difficult, kind of the stretch goals of S-mode. And those are to quantify the role of air-sea interaction and surface forcing in the dynamics of the sub-mesoscale variability, and to diagnose the dynamics of the vertical transport. So that is measure W and try to understand the dynamics of vertical transport at sub-mesoscales. So we conducted the pilot campaign last year. This is kind of the tracks of the various assets. We put a lot of focus on this area here and conducted what we called a velocity extravaganza. And so now I'll start to show you some of the data from the pilot campaign. And we've compared many different kinds of velocity measurements to others, and there's still more work to do here, but here are some of the preliminary results. So this is a comparison that Luc Lenane and his team have done between the wave gliders, which had an upward-looking ADCP and a downward-looking ADCP, to .viz. So I mentioned that .viz can make these estimates of the vertical shear by looking at different horizontal wavelengths. And this is one comparison between the dot-viz estimate, which is kind of covering the upper meter, and the upward-looking ADCP, which is stops around 1 meter and goes from something like 8 meters to the surface. And here's a comparison in this red box between all the co-located dot-viz and waveglider measurements. So this looks really pretty good. We expect there to be natural variability in addition to, due to vertical shear, in addition to the instrument error. And so I think this is a really satisfying comparison between dot-viz and the wavegliders. Here's a comparison of Doppler scat and dot-viz. This is after retuning the geophysical model function for velocity from Doppler scat. I think this is also really encouraging. There is, noise that's maybe on the order of 10 centimeters per second here in the point-to-point comparisons, but it's really encouraging. There is some work to do on the model function for Doppler scat. I think so I mentioned that those data were tuned to the dot-viz data. And this is a comparison between Doppler scat and the in situ measurements on those days when Doppler scat was trained on another data set, and it looks pretty good. But when we compare Doppler scat to all of the in situ data, it's still not bad. It's definitely correlated, but there are some outliers that suggest that we're, one interpretation is that we're experiencing conditions here that are outside the training data set of Doppler scat, and that the model function is not dealing with those correctly. Nonetheless, the estimates of quantities like vorticity from Doppler scat are seem to kind of carry over from one flight to the next. And I think this is the really exciting thing about Doppler scat, is that we can start to produce maps of quantities like vorticity and divergence. And so here we're seeing flights over the same region on 2 different days, separated by 2 days. And this is vorticity normalized by F. And you can especially see this feature, and this feature was visible in sea surface temperature as well. And it's trackable from one day to the next. We also had airborne SST imagery on the same aircraft as Doppler scat and on mass. So Jerome Mullenmaker is the PI on this Moses instrument, and it's capturing some really high resolution imagery of the sea surface. So this is, on the left is a satellite sea surface temperature image. The 5 black dots were sail drones sampling near this front. And this little vortex that you can see rolling up there is shown here in more detail in the Moses imagery. So for a sense of scale, this is about 10 kilometers, 2 ticks. So 1 tick is on the order of 5 kilometers. So these are really small scale features that we're seeing here. Luc Linane provided this plot, which shows combined SST and Doppler dot-viz surface currents. And it's really exciting to have this kind of synoptic scale imagery with, for example, here, a sharp front in SST and in velocity. And just zooming in on this front, you can see the sort of richness of the data set. You can even see little striations in the SST from Langmuir circulations. Mara Freilich has been analyzing these data to look at kinetic energy flux. Mara will talk in, I don't know, in a month or so in this seminar series. And maybe she'll talk more about this, but she's computed the energy flux from larger scales down to scales below 512 meters. And the top panel shows an estimate of that kinetic energy flux. The bottom panel is this SST front, and you can see enhanced transfer of energy to smaller scales there. Here's another example from a much weaker front, but again, you see what looks like enhanced kinetic energy flux related to these sort of SST frontal features. Presumably, these are fronts. I wanted to talk for a few minutes about something that's kind of a challenge facing S-mode, which is that we aspire to make measurements of W vertical velocity, but then what do we do with that after we measure it? Here are measurements of vertical velocity that Eric Desaro and his collaborators collected during Calypso, an experiment in the Mediterranean recently. You see that it's extremely stripy, and that's not noise, that's internal waves to a large extent. And the horizontal velocity is just dominated by inertial oscillations here. So you have really just 4 or 2 complete oscillations of the inertial currents. So if we zoom in on this vertical velocity and look in more detail, you can see the internal wave character. Velocity is negative, float goes down. Velocity is positive, float goes up. And, you know, that's interesting vertical velocity signal in its own right, but we don't think that the internal wave vertical velocity signal does very much vertical transport. It's just moving things up and down as an oscillation. So one thing that we might try, and Hector Torres has been working on this idea of a dynamical filter by trying to exploit the properties of internal waves, which would have a vertical velocity profile that does something like this, going from 0 to a larger value, at least for the low vertical modes, would go from 0 to a larger value near the peak of the stratification, and a horizontal profile that looks like this. So if we just take the velocity, the vertical velocity at the base, and kind of go linearly to 0, we could try to filter out the internal waves. And this is the result of doing that. So you can see that it largely reduces the internal wave vertical velocity signal, but some other signals are retained. and this one we think is a sub-mesoscale vertical velocity signal in the Calypso data. I wanted to ask this audience and about what statistics we could measure in S-mode that would be the most meaningful test of the model predictions and dynamics. I really like this paper by Balwada et al., who did this technique of sort of filtering model simulations by vorticity and strain. So this plot is vorticity on the horizontal axis, strain rate on the vertical axis. And this is vertical velocity in the colors. And you can see that there's intense upward velocity in these negative vorticity features, or negative relative to F, whereas we have like a distributed downward vertical velocity. And I think this is really interesting. Balwada et al. Used this kind of, then filtered in this space to sort of see what kind of features in the simulation were providing these signals and these signals. But I think that this could be an interesting way forward for looking at statistics that we collect in S-mode. But we could plot things like frontogenesis forcing in vorticity strain space. Anyway, I would be interested to know what you all think would be interesting there. So right now we're starting the first intensive observation period. We have 5 UW gliders with ADCPs, 8 other gliders provided by the U.S. Naval Oceanographic Office, and 8 wave gliders, 4 sail drones, 75 drifters, and 3 aircraft making remote sensing measurements, and a research vessel, all about to deploy. The data from the pilot campaign are being released on PODAC now, and all are welcome to use them. And that's all that I wanted to say in this presentation.
Thank you very much. This was great, Tom. Questions for Tom? While people are thinking, I'll ask a question. I was really struck that at the beginning you talked about a goal of having very accurate velocities on the order of a centimeter per second or better. But your comparisons of different measurements are not showing that, but you say you're looking at large scale gradients. What do you think the limits are for the aircraft measurements? And is that absolute velocity goal aspirational or in range after a little more analysis?
Good question, Sarah. Well, I think that the wave gliders are meeting the goal. We think that we can make centimeter per second accurate measurements. And this accuracy, we'd like to have a centimeter per second accuracy over a kilometer. A lot of, and I would say that's the random error that we're going for. Bias errors, as long as for something like Doppler scat, the bias errors are correlated over relatively large distances. So that when we compute things like vorticity, I think a lot of that will drop out. So maybe another way of saying that is I think Doppler scat has larger bias errors than random errors. And so those are related to things like the wave field, or, I'm not really sure, but to large scale factors. Mass, I wouldn't be prepared to put a number to it, but I think that mass is, or DOPVIS, this technique that Luke Linane is using, I think it's pretty accurate. The measurement physics are pretty straightforward.
So when you do the intercomparison of the two, you're thinking that DOPVIS is the more accurate measurement at this point?
Yes.
Thanks. There's a question in the chat from Yuri Simoes. Sousa, do you want to unmute yourself and ask, or should I read this?
Yeah. I just got curious if the next expedition will coincide with the fast sampling phase from SWAP.
Yeah, the April campaign, the final SMO campaign, should coincide with the fast sampling phase of SWAT. It's in the SWAT one-day repeat orbit crossover. Let's hope that SWAT launches on schedule. I see.
And Dudley has a hand up.
Yeah.
Hi, Tom. Great
Hey, Dudley.
presentation. Thank you. So you showed a map of the vorticity that you calculated from Doppler scat. And I think that you said that that was a case study example when there was some outliers in the velocity estimates themselves, which would be consistent because the vorticity maps look pretty reasonable, or the map that you showed in comparison to SST. So that would seem to be consistent with your statement a few minutes ago that the errors are pretty large scale.
Yes.
So I was wondering if you were brave enough to look at surface divergence.
Yes. Well, Ernesto has been looking at that, and the divergence has a lot more artifacts. I don't know why that is. Maybe either Ernesto or Alex Weintier could comment.
So I can pitch in on that a bit. As Tom mentioned, most of our, if you look at a pitch of ocean, if you look at the random component of the errors, by the time you average down to a kilometer and a half, something like that, we are at the centimeter per second scale in the random part. So the things that remain right now are in removing those wave effects that Tom talked about, that we call the geophysical model function. And that is purely right now an empirical process where we have to use training data from DOPVIS, for instance, to remove some of that. And the problem has been that there isn't a whole lot of training data so far. And there are fluctuations in addition to the wave processes where you need a lot more training data in order to fully remove those things. And why divergence is affected more strongly than relative vorticity has to do with the fact that in the way we collected the data, the divergence was governed by a component that of the velocity that was crosswind. And that crosswind component also has the highest errors at the edges of the swath. And so there were biases at the edges of the swath that show up. And so by removing parts of those edges, you can actually remove a lot of those errors at the expense of removing part of the signal. But that's something that we're working on. So I think in summary, the biggest challenge, I think, for Doppler scatterometry is removing all those wave effects and wind effects, requiring a training data set because the hydrodynamics is very complicated and there's no direct way of removing them using just theory.
Other questions? Thanks, Ernesto. Melanie has her hand up.
Yeah, hi, hi, Tom. Interesting talk, thanks. I guess I have sort of two different questions. One, do you think that, and maybe this is more of a question for Ernesto and Alex, but do you think that the errors you were just talking about are related to the age of the wave field? And like, do you see differences in those errors?
So we had an experiment that we conducted off of ACIT, the AC Interaction Tower, and we did correlation with wave age. Wave age actually was very weak part of it, and the reason is that we're mainly responsive to half-centimeter capillary waves, and so really the presence of very long swell is very weak modulator on those waves. So it's much more related to just the wind input rather than the wave age.
I see. Since no one else has their hand up, I guess my other question for Tom or for the team is, I was wondering if you could talk a little bit about what people will be doing with all those interesting hyperspectral measurements.
Well, there are different things. I mean, on the one hand, there's interest in how the sub-mesoscale vertical currents and other ocean dynamics modulate the nutrients and, you know, primary productivity. On the other hand, ocean color is, you know, a useful tracer of the dynamics. So I think, you know, it's some of both. I think there are a lot of unresolved questions about these like really spectacular patterns that you see in ocean color at the sub-mesoscales. What's driving those? You know, is it just the ocean stirring things, or is there a biological response to the sub-mesoscales? And I'm sure it's probably all of the above. But so those are some of the science questions embedded in S-mode, but it's also a really great sort of tracer for the flow field, though imperfect, like all of our other tracers.
Yeah. Can I ask you another question since no one has their hand up?
Go ahead.
Of course.
So you showed that one feature that off San Francisco Bay, the positive vorticity feature, and then you said 2 days later it's still there. And was I reading the scale right? Like, I'm astonished that something could move only 10 kilometers in 2 days. Did it move away and then come back potentially?
It probably did. I mean, the inertial currents are really moving things around. In fact, that's one of the big challenges with the autonomous platforms. You know, we have this array and we want to measure some front, but you know, it's just moving a lot.
Yeah.
So I don't remember on that particular instance, but I wouldn't be surprised if it was moving. We sort of experienced that while we were trying to track things.
Do you think that that feature was San Francisco Bay plume front or something else?
I think, I don't know, you know, how to answer that. I think it was this kind of part of,
Okay.
I think this part of the SST field corresponds to that feature that we were seeing. This is where we were making measurements, but this was a few days later, 2 days later than those Doppler scat measurements.
Okay, so maybe more of like a plume of recently upwelled water from Pointer.
So Tom, I think for those particular days is the area you have circled
Here.
there.
I was looking Yeah, you might be right, Ernesto, but I was trying to, yeah, we still have some analysis to do for sure, but so 37.5, 125, maybe you're right, Ernesto, 125, 37.5, yeah, it's here. In any case, there was a SST signal associated with that front that we had seen.
Yeah.
So Ernesto, you think that's right? Yeah. Okay.
Is there a lot of clear sky SST to look at its evolution from day to day?
Not a lot. I mean, there was over the month, there might have been 6 really good images like this.
Right. So not enough to track its evolution day in, day out.
No, but we did have, yeah, I mean, that is true. No, there's a data similar to a model that NRL is running that was pretty skillful at even predicting features like this. And it can help us fill in the blanks on where these things are at. I wanted to comment on Dudley's point that, despite the noise, the vorticity looks pretty okay. Or, despite the bias errors, the vorticity looks pretty okay. I guess that was something we expected when we were proposing S mode, and it's one reason we went for thought of a campaign where we could use Doppler scat and look at velocity differences instead of the absolute value because of concerns about potential for bias in the retrievals.
Mm-hmm. Well, we are at the end of an hour. This has been really great. So a big round of applause for Tom, and thank you very much, everybody, for joining in this discussion.
Thanks, everyone.